I'd like to remind you of the last theorem I had on the board. Which gives a sort of presentation of the zero slice of algebraic Bordism and can be used as sort of a basis for other computations. I want to for listing these other computations, I would like to have this on the board. So we have iron. So this is over a field of characteristic 0. We have the algebraic Bordism spectrum, which is effective, and the map to the zero slice can be identified with the map to the following quotient, where these are the generators of the Lazare ring. And let me list a few consequences. So one consequence is if you compare sort of the sphere spectrum and MGL. You have a unit map for the ring structure here. This here induces an iso on the zero slice, and this follows from the theory of orientable theories. This is motivic homology, and I would like to briefly explain this relation between the zero slices. For this reason, I would like to introduce a filtration on this spectrum, and this is the obvious filtration. You start with the zeroth space in this spectrum. So this is the tomb space of the zeroth, the rank 0 tautological bundle on the zero Grassmannian. It's a very complicated way of saying that this is a space consisting of 2 points. Yeah? And then you continue to suspend. This is the 0th step, and as you can see, this is just the sphere spectrum. And in the first step, we have the tomb space of the first tautological bundle, line bundle over the Grassmannian of one-dimensional subspaces, so this is P infinity, and then we suspend from there. Yeah, and you can iterate this in the obvious way, and in the end, as the co-limit of these, you will get MGL. And sort of just to clarify what type of spectrum is this, well, it's as with sequences in real analysis, it doesn't really matter what's here on the first few spots. What matters is what happens in the end. And yeah, as one can check, if you compute the tomb space, so that's the quotient of the complement of the zero section in the whole bundle. The whole bundle is equivalent to this space, which is P infinity. The complement of the zero section is contractible. So this here is actually a -2, -1 suspension of P infinity. Okay, and now in order to get this isomorphism, we use that the slice functors are triangulated, in particular the zero slice functors. So we can look at the unit map and take its cone C. And what we have to do in order to prove this isomorphism, because both are effective, is that this here is to 1 effective. So this here is the question. And in order to compute this, you can compute the iterated cones that you get from this filtration. Let me be sort of a bit sketchy, of course, and let me just look at this first case here. This is the identity, and here something happens. This here is equivalent to P1, this here is equivalent to P infinity, and the map you have here is the inclusion. And from then on it's suspensions. So at this stage we're looking at the inclusion of P1 into P infinity, and again, if we want to understand this, it suffices to look at a finite stage first. So we have an embedding of n-dimensional projective space. Yeah, here that's the co-limit of these as a space, and this here we can express as follows. Maybe, yeah, I should have. Yeah. Okay. So take the linear embedding of what I have to do. Wait. This is true. Yeah, maybe it's true. Okay. Yeah. N minus 2 in here. And this is the open complement. And one can find or factor this embedding here such that this map is the zero section of a vector bundle.
Which map are you using from P1 to P8? You're just choosing one coordinate for P1?
Yeah, this is the standard embedding.
Okay, so
yeah, standard linear embedding. Yeah. This, I mean, it's the one which corresponds to the unit map here. Okay. Right. So this here is the zero section of a vector bundle over P1. So this is an A1 equivalence, and if we want to compute the cone, the quotient here, it suffices to compute the cone here. And for this we have homotopy purity. Yeah. So the cone this is equivalent to the tome space of the normal bundle of this this inclusion. So Pn minus 2 in Pn. Huh? Okay, so this is codimension 2, so it's a rank 2 bundle. So the tome space locally looks like a 4-2 sphere. Okay, at first sight this seems to be more than we need, yeah? But it's not, because we're here in the first stage of a spectrum, so we actually have to desuspend here. Yeah? Okay, so this shows that the cone here is contained here, and you can do this similarly for the other steps. You have to include a suitable Grassmannian in a higher dimensional Grassmannian, and there's a similar geometric argument, but I should not embarrass myself by trying to write down the details correctly. Yeah. Okay, so yeah, you might not have noticed, but this argument here that the cone is contained in here, this works over any base. But for the identification of the zero slice of MGL with the motivic homology spectrum, we use this statement in characteristic 0. Okay, so this is one illustration. But that the zero slice of the sphere spectrum is motivic homology, Mark Levine proved this using other methods over any field. Yeah. In this spirit, one can also derive a similar theorem, which is again true for any field.
So this corollary holds over any field. You're saying that this corollary holds over any field. Because of the
this holds over any field, and this isomorphism holds over any base. Yeah, for example, with this relatively new theorem of Bachmann-Hoyoa, that the zero slice of this is this over a Dedekind domain. Yeah, we have a similar statement, but we still don't have this explicit. No, I don't think we still have this. We have this explicit presentation. Then there's more work involved in that. If I remember correctly, but okay, yeah. Just because it was mentioned in some detail in Matthias Wendt's talk, what we get from here is a computation of the slices of algebraic K-theory. So the graded slice of algebraic K-theory is motivic homology adjoined a periodicity element. And I'll sketch a proof in characteristic 0 using this argument. Again, motivic Landweber exactness gives you that KGL can be described as follows. You take MGL and then you quotient out the generators of the Lazar ring x2, x3 and so on, and you invert x1. Yeah, this can be checked. Yeah, from this, this computation then follows. Yeah? And why do I want to have this isomorphism? Yeah, it was also mentioned in Jonas' talks. So the spectral sequence you get from that is the motivic spectral sequence. Yeah? The motivic slice spectral sequence, which has been analyzed in detail. There's Bloch-Lichtenbaum, Friedlander-Suslin, Grayson, Kakusha-Panin. Yeah, so this is the motivic spectral sequence. Right, and I should also mention at that point that this here is, of course, very similar to a motivic Corner-Floyd theorem. So Vanya is not here, so maybe it's better to say this when he's not present. So there's this Corner-Floyd theorem for KGL, and this is a joint work with Vanya Panin and Konstantin Pimenov and myself. But I would like to stress that as you know, Vanya and his generosity, it's really his contribution should be emphasized a lot. Yeah, and he allowed me to join into this beautiful project. And in fact, while working with Vanya, I've never seen Konstantin Pimenov at all. Yeah, he's not present, is he? No. Okay, he's not present. Good. Okay, so there's a sort of different approach than this motivic Landweber exactness due to Naumann-Spitzweg-Östwer. Okay, I wanted to mention one more consequence, and this is due to Spitzweg. then again in characteristic 0. And using this presentation of the zero slice, one can describe the whole slice filtration on MGL using explicit co-limits of diagrams involving the generators of the Lazar ring. And in particular, one can describe the graded slice. Maybe I'll try it like this. So the graded slice is, no, I can't, not now. So the qth part is the 2q suspension of motivic homology tensored with the Lazar ring contribution in degree 2q. So morally, the statement is that the graded slice of MGL is HZ tensor the Lazar ring as a graded object, and then you have to suspend appropriately. So this is one thing you can more easily remember. You're about to.
What's the notation for QQ on the Lazar ring?
Yeah. So this is of course a very awkward grading, but I would like to have xi grade 2i, I. So it's really just z graded, but written down to correspond to the motivic geometric line in the motivic bigrading.
So when you write 2QQ, you localize this with the you take the 2QQ graded piece.
Yeah, so for example, I meant to write this down anyhow. So the one slice is this here, and this is generated by x1, and the 2 slice, this is a 4-2 suspension of integral motivic homology generated by x1 squared, but then you have another 4-2 suspension generated by x2, and this goes on. So we know all the slices of MGL, and this is very convenient. I forgot to mention one thing. I didn't write down the spectral sequence for the motivic spectral sequence in this case, but maybe it's not. Maybe it's not so important. Okay. So one can use this computation of the higher slices of MGL to get a computation of the whole slices of the sphere spectrum. And before doing that, yeah?
So in this theorem of Spitz-Weg, suppose I replace SG by S0 or S0 of MGL. Does it hold over any characteristic?
What Spitz-Weg actually
used here in this theorem? Just
yes.
Zero slice with SG or something?
No, it is what is really used is this explicit presentation. So the theorem that Markus Spitz-Weg states, because he likes to do things over some base, is suppose the Hopkins-Morel isomorphism holds over a base. Yeah, so this presentation here. Then you get this here over a base. And for example, Hoyoa proved this Hopkins-Morel isomorphism in positive characteristic, provided you invert the characteristic. So this here holds in positive characteristic. You just have to invert the characteristic here and here. And conjecturally, it holds over any, let's say, regular connected base, maybe something like that. Yeah. I think this is what Wowodzki states in his open problems paper. Does this answer your question? Okay. Okay. So in order to get at the slices of the sphere, we use the sort of the Adams resolution, but it's now a motivic version, and it should be called the Adams-Novikov resolution, of course, because it's a Bordism type resolution. So we have the unit, and MGL is a ring spectrum, so we have both left and right units. We also have a multiplication, and you can iterate this. So this is motivic Novikov solution, and of course formally you can apply this to any motivic spectrum. You smash this diagram with a given motivic spectrum, and yeah, maybe at this point, before I sort of forget, no, not forget, before time gets precious in the end, let me state that, of course, one can use motivic homology instead, and for example, motivic homology with finite coefficients. Then we get motivic Adams resolution, and since this is about computations, then in the end for motivic stable homotopy groups of spheres, I would like to mention that there have been many computations already. For example, using the Adams resolution by Duggar and Isaacson. So there are computations for the complex numbers and for the real numbers, and I think using Adams-Novikov there are computations by Ormsby and Östwer over, I think, what they call small fields, so something like QP. There are yeah, I should probably mention more names here. So this is sort of then giving only a specific part of the motivic stable homotopy groups of spheres, and this is actually a subtle question to what this then converges. In contrast, I would like to mention the following beautiful theorem, which can be thought of as an analog of Serre's theorem on finiteness on stable homotopy groups of spheres. Right, and before stating this theorem, I have to explain some notation. So what they prove is that if you take any field and you take a certain part of the rationalized sphere spectrum, this is the minus part, and they prove that it's equivalent to the Eilenberg-MacLane spectrum corresponding to the rationalized sheaf of Witt groups. And in particular, this gives a statement on the motivic stable homotopy groups of spheres. It implies pi what do I have to say? N plus Q, Q I is torsion for n greater than 0 and Q greater than or equal to 0. I hope I stated this correctly, but fortunately, yeah. So what really enters in a substantial way this computation is sort of determining the width theory cooperations, which has been done by Alexei Ananievsky. Let's see. And what is this notation? So if we rationalize any motivic spectrum, then it splits canonically into a plus part and a minus part. And these correspond to the idempotence I plus epsilon half, I minus epsilon half, where epsilon corresponds to the twist isomorphism on the smash power of the multiplicative group with itself. Okay, and I wrote it down in the wrong order, of course. I should write it like this because minus corresponds to plus, plus corresponds to minus. Yeah. Okay, this here is known to be motivic homology, rational motivic homology, and this was determined here. Okay, so this was sort of a small detour. Now, the determination of the slices of the sphere spectrum. So this has been done by Mark Levine, following Powotsky's open problems paper, and I would like to add my name as well, together with my long-time colleagues, because we refined this in a certain sense, in particular regarding the multiplicative structure. So the Q slice of the spheres, I should say this. So this is characteristic 0. The same statement holds over positive characteristic fields if you invert the characteristic, yeah, as was discussed previously. So the Q slice of the sphere spectrum is a 2Q. No, let me write it down like this. We have a sum indexed over natural numbers. It will only be finitely many, don't worry. It's a 2Q minus P comma Q suspension of HC tensored with a certain group, which, except in one degree, is always a finite group. And this statement is due to Novikov. And it is the E2 page of the topological Adams Novikov spectral sequence based on complex borders. Yeah. So, as in the case of, and I should state this. This is suitably multiplicative. Yeah, if you look at the whole graded slide.
AMU is topological.
It's the topological.
Mm-hmm.
Yeah. It's the topological complex Bordism spectrum, which happens to be, I can of course define it as the complex realization of MGL. Yeah. As if they didn't start the whole thing. Yeah. Okay, so for example, the one slice is the 1-1 suspension of mod 2 motivic homology. The 2 slice is the 2-2 suspension of mod 2 motivic homology, and then there's a 3-2 slice, 3-2 suspension of mod 12 motivic homology. 3 slice I can go on for a while. I don't know if you want to stop me, but I'd like to write down the last summand here. This is a 7-4 suspension of HC mod 240. Yeah, so the Bernoulli numbers come up, and of course they come up because they describe the order of certain elements, the so-called alpha family. Okay. Let's see. Let me say a little bit about the proof here. So, you have the sphere spectrum here, and then this co-simplicial diagram, which you get from the ring structure on MGL. And you might wonder, well, if we take the homotopy limit of this diagram, does it give the sphere? And the answer is, well, in general, this is not the case. But what happens on the level of slices is the following. If you want to compute the Q slice, this is actually the homotopy limit over delta, and then take the Q slice of the appropriate smash powers of MGL. So I'm not saying that I'm commuting a homotopy limit with a slice functor. This is in general not possible. There exist counterexamples. So how do you prove this here? So one thing you do is, so for example, if you look at the cone here, this we did before, then this here has higher effectivity than these two. Yeah. And if you insert, instead of the sphere spectrum, MGL, so you smash this with an extra copy of MGL, the homotopy limit has a very simple form, because, yeah, imagine smashing this with an extra copy of MGL. Then you have the sort of the action of MGL on itself, which can be used to split this co-simplicial diagram. Yeah, so the homotopy limit is then just the sort of the initial term, and this sort of passes through also on the level of slices. So what you do is, I mean, this is just the first stage, but you can iterate this and get higher and higher effectivity in the cone here. If it's high enough, then it will vanish on the Q slice. So you can start a downward induction with trivial objects and work your way down to get the statement here. Yeah? So this is 2-1 effective. Okay. What does this give us? Yeah, let's see. All right. I should mention this. Where is it? Ah, it's here. Okay. The theorem of Markus-Spitzweg, which is on the board here, this has a straightforward extension to smash powers of MGL with itself. So for example, when you have a twofold smash power of MGL with itself, you can describe then the slices using the appropriate Landweber-Novikov algebra appearing there. So the general description, where is it, would be that SQ of MGL what should I say here? Maybe M. Yeah, if you take the M plus fold smash powers, then this is the appropriate suspension, where here you take the 2qth homotopy group of the appropriate suspension of the complex Bordism spectrum with itself. Yeah? This is follows from Spitzweg's theorem. And then you apply the homotopy limit on both sides. Yeah. And what you have here, so the homotopy groups here can be determined, and what you get here is sort of a certain degree part of the sort of the total complex you get from the topological Adams-Novikov resolution, which is a free chain complex. So you can sort of move this this smash power out and get that this is equivalent to 2qq smash hz tensored with this whole limit of this diagram, and the standard notation is then that this is a certain total complex. And sort of the homology of this complex is what computes the E2 term of the Adams-Novikov spectral sequence. So this X group that I wrote down there. So what you have here is a chain complex of 3 abelian groups, and you would like to relate this to its homology. Yeah, but since the integers is a, what do I have to say, principal ideal domain, yeah, any chain complex is quasi-isomorphic to its homology. Yeah. So you can replace this here with
zero differentials.
Yeah, with zero differentials. I say isom to what I wrote down there. X and U star, and U star, and U star, and this was sort of in this degree 2q. And this proves the statement. And if you want to check that this is suitably multiplicative, of course you have to pay extra attention to the ring structure that is induced basically from the ring structure of MU. Okay. So what we have.
So I guess the first part of that proof has nothing to do with characteristic, right?
Pardon?
The first part of the proof that isomorphism that has nothing to do with characteristic, right?
You mean This here. This is independent of the characteristic. Yeah, this is just this effectivity argument and formal properties. So this is again yeah, this is again formal. Yeah. So I mean, as I mentioned, this theorem has a positive characteristic version. If you invert the characteristic, it seems that you are secretly thinking what happens at the characteristic.
Yeah, I mean,
Okay. Well, maybe we two can have a conversation later. Yeah.
And, sorry, if you don't invert this characteristic, the problem is with the resolution of singularities or something else?
So one problem is the Hopkins-Morel isomorphism.
And what does it depend on?
It depends on the determination of the Steenrod algebra. So if you knew that the Steenrod algebra at the characteristic had the usual form, the motivic Steenrod algebra.
Do you think it is? It does?
There are people who think it is. Yeah. Yeah. There are people who work on proving that it is. Yeah.
Okay.
Yeah. So, of course, yeah, determining this motivic Steenrod algebra at the characteristic. I mean, in characteristic 0, it involves resolution of singularities. In positive characteristic, away from the characteristic, you can use the LDH topology, as developed by Gaba, Kelly, Cieszynski. But sort of these obvious methods, they do not give you the Steenrod algebra at the characteristic. Yeah, what Spitzbeck and Franklin proved is that the motivic Steenrod algebra at the characteristic is at least as big as the expected thing. And conjecturally, the other summand is 0. And if you have that statement, this statement here, for example, and the Hopkins-Morel isomorphism, they hold for any field. And some people are already speculating what then happens over a Dedekind ring, things like that. Okay? Yeah. Thank you. It's a very reasonable, a very good question. So, maybe, since I have some space here on the board, I should mention a fact that has been mentioned in Jonas Krilling's talk yesterday already. So, we have, I mean, for any motivic spectrum, we have Blavatsky's slice filtration. So the Qth cover maps naturally to E, and this here, yeah, maybe I should write down the whole tower. We have the Q plus first cover mapping here. Yeah, so this goes on, and you can look at the homotopy co-limit where Q goes to minus infinity of these, and this turns out to be E itself, and one explanation for this is this little lemma that I proved about the compact generation of the motivic stable homotopy category. Yeah, I mean this essentially covers this, but I mean this goes also on in this direction, and you might wonder what happens here. Yeah, so the homotopy limit where Q goes to plus infinity, Q of E. Yeah. What is this? And let me give you two examples. Yeah. One example, this was described by Wygotsky. You take the mod 2 Eilenberg-MacLane spectrum, and we have a certain element. This was also mentioned by Jonas. So this is okay. Yeah, let me take a field Z mod 2 coefficients twist 1, and let's assume that the characteristic is not 2. This here element is -1. Yeah? And what you can do in this spectrum is invert this element. You know? This is a non-trivial spectrum. It represents étale cohomology in the motivic stable homotopy category. So I guess we all agree that it's non-trivial, but due to its construction, you form this co-limit where you suspend, continue to suspend with the GM. So this is effective. Let me write it like this. This is to QQ effective for any Q. Yeah. So in particular, this filtration here is, it's fairly uninteresting. It's constant. Yeah, and in particular, this homotopy limit here is non-trivial.
The result holding is non-trivial.
Yes. Yes, the homotopy limit is non-trivial. So the diagram is constant in this case, so the homotopy limit of these FQs is just the spectrum itself, which is non-trivial. And
are there cases where we know that this is trivial?
Yes, there are cases. So one case, this also follows from the sort of Spitzweg's analysis of the slice filtration on MGL. I did not introduce this formally yet, but on the motivic stable homotopy category, there's another filtration, in fact a T structure, Morel's homotopy T structure. And sort of measuring the connectivity with respect to homotopy groups, just said very roughly. And in the case of MGL, the Qth effective cover is Q connective with respect to the homotopy T structure. So if you take the homotopy limit where Q goes to infinity, this is contractible. And if you like, you can replace MGL by KGL. This is, in some sense, the strong convergence statement for the motivic spectral sequence on algebraic K-theory, which was mentioned also yesterday in Jonas' talk. Okay.
Just a stupid question, please. Is the spectrum with inverse?
Yeah.
Is it not effective?
Yeah, it's very. It's. I have to. I have to.
Even very. Okay.
No. I'm not saying that it's. Sorry. Am I saying this? I meant to say it's very effective in the sense that it is Q effective for any Q. Yeah.
Yeah.
But it is also very effective and very Q effective for every Q. Yeah. I did not introduce the very effective slice filtration yet. Yeah. Okay. Is this?
Is there a general criteria for knowing when the limit? So is homotopy limit vanishing being contractible or not is related to the convergence of the response to the sequence?
Yes.
Is there a criterion for, or we have like general criteria?
You would like to have a more general statement.
There are examples, right?
Yeah.
KGL or...
Yeah. I meant to give you one further example, but while erasing the board for that, you can have the following fairly general, but of course not very general statement, is any Landweber exact motivic spectrum is slice convergent in the sense that this homotopy limit vanishes. But yeah, for example, how should I stick this? Let me just give you another example. Right, maybe the following example. This is a spectrum which was already on the board yesterday in Jonas Skilling's talk. You can describe it as the Hermitian K-theory spectrum. Some people prefer to call it KO or even BO. It has several names, and this name is disliked by many people. I still use it, yeah. And of course you have to invert eta. And one can check the following. For example, KW mod 3. This is a motivic spectrum whose slices are all trivial. This follows from the computation of the slices. So, all right. Here we're over a field characteristic not 2. Q is any integer. Yeah? So again, in this case, the slice rotation is constant, but if your field is formally real, again, this is a non-trivial spectrum because it represents Witt groups modulo 3. So, for example, for the real numbers, it's non-trivial. So this already illustrates if you have a motivic spectrum where some version of Witt theory is involved, then you might get a problem with this homotopy limit. And so, for example, for the sphere spectrum in general, this homotopy limit is not trivial. So,
so it belongs to the intersection of all FQ SH.
Yes. This is also, super effective.
Wow.
So KW represents what in general?
KW represents Balmer's higher Witt groups. Let's say over, what do I have to say, over a regular base scheme in which 2 is invertible, and maybe it's even true more generally. Yeah, I don't know. I'm not sure. Yeah. Okay. What? So this is about the homotopy limit of this diagram, and one can look at this homotopy limit sort of from a different perspective. You have FQ of E mapping to E, and you can take the cone of that, and if you are again a fan of not very elegant notation, you can call this F upper Q of E. But maybe it should rather be F upper Q plus 1, I'm not sure. So for example, F upper Q minus 1, because for example for the sphere spectrum you have the first effective cover and then the cone is the zero slice. Yeah. Just as one example, if your spectrum is Q effective for some integer Q, the first non-trivial thing you will have here is the bottom slice, and then if you go up, these spectra can be described by sort of iterating, attaching the slices. Yeah? So this, if E is sort of Q effective for some Q, I should not say Q, N effective for some N, this is sort of a finite extension of slices. And you can go to infinity, and then you have here this homotopy limit of the FQs of E. You have E, and what you have here is also the homotopy limit of the F upper Qs. And let me call this the slice completion of E. Yeah, this appeared in Jonas' talk yesterday, and somehow by construction, the motivic slice spectral sequence computes this spectrum. Okay. And yeah, maybe this is one type of general theorem, but it's actually very special. Yeah, I must apologize for that. F is some field. If E is a motivic spectrum, which is cellular of finite type. Then the slice completion can be identified with the eta completion of the spectrum. And this is the homotopy limit over sort of powers of the Hopf map eta. Yeah, I did.
Sorry. So cellular in this context means it is constructed by attaching finitely many cells, or
no,
cellular of finite type.
It is cellular of finite type. You are allowed, if you watch out a bit, to attach infinitely many cells. Yeah, but you have to start at a certain weight, and in every given degree, every given weight only finitely many. So let me give you one example. MGL, this is cellular of finite type, but it's not a finite spectrum.
Yeah.
Yeah. So yeah, I don't know. So being cellular, I should rather say being stably cellular. I mean, this notion was, I think, first coined by, in this context, by Dagger and Isaacson. So it is what you can build using just standard topological cells in this sense. So basically what you can get from the sphere spectrum, you can think of this as sort of being Tate motifs. I forgot, you also had a question?
No, it's fine now. Yeah,
it's fine.
I just want this slice of E. No, Holim is a kind of obstruction for E to be.
So we would like this slice completion to be the same as E, but in general it is not.
Yeah, and Holim is obstruction for this.
This homotopy limit is the obstruction. And yeah, with this theorem we sort of have a different description than of the obstruction, namely this is the fiber of the map to the eta completion. Yeah.
So and therefore, for example, MGL as a cellular spectrum is for lim of E mod eta to M.
Yes.
MGL over eta to M.
Yeah. So okay. I mean, this is sort of rephrasing things which have been on the board already, of course. The Hopf map is 0 on MGL, sort of by construction, and therefore it is eta complete. Yeah, for obvious reasons. Yeah, yeah. So, yeah. But I should maybe emphasize this spectrum here, KW. This is cellular, and then also KW mod 3 is cellular, but it's not a finite type. Cannot be. Okay, I think my time is up. Yeah.
Can you say again 2 words about this EBT argument, the one is still on the board, for computing this Q slice of series spectrum?
About this here?
That line with the root is okay.
Yeah.
So then how do we slice?
So let me call this MGL bar. What you do is you then smash this with MGL bar. Oh. Okay, so you do this as many times as you want.
You can compute the slope here.
Yeah.
Compute the slope from the diagram, and this will show the general strategy.
Yes, this is the strategy. So this here is for. Yeah, you can compute the 2 slice from that. So I mean, this here is for 2 effective. Yeah, because this here is 2-1 effective. And you can increase this if you like, but you then have, no, maybe not, let's say sort of the 1 slice of this is the same as the 1 slice of this. This here is an MGL module. So this homotopy limit splits. And then you can compute the homotopy limit in the case of the 1 slice, and this then gives you information about the information you want about the 1 slice of the sphere. This is sort of the downward induction that I mentioned. Okay, so maybe we should this MGL module, the whole limb splits. Okay. Further questions?
Lector.